Okay, friends, welcome back. Now we are discussing about matching networks. So, from the very beginning, our main intention is to match ZS is equal to Z naught. That means RS The RS is connected to lossless LCM. LCM in sense inductance, capacitance, and mutual inductance, that is transformers. And RL is equal to RS, then only the maximum power will be transferred from source to the load. So, which networks we have to choose? So, why we have to choose these networks? So, mainly these networks are chosen in order to match if there are any mismatchings in the networks. Okay, simply by choosing L, comma C, comma M. Lossless mean any element that does not consume power. So here lossless means that we do not consume any power. Okay, that we do not consume any power. Suppose I did that lossless network and put in between source and load. I mean lossless network in sense LCM. Either it have maybe inductance, capacitance, or transformer, and then maximum power will be transformed from source to the load. Zn is equal to Rs, matching network. Suppose we can achieve this by we can get maximum power. Okay. Suppose we will achieve the matching network, then we have to get the maximum power. So for the matching network, we are taking here mutual inductance, that is transformer. So how the transfer, what is the input impedance for this both? Okay. So here the source voltage is there, source resistance is there, primary voltage is there, N is to 1 transformer turns are there, and how the transformer and how the current and the voltage will be V2 and V1 in the secondary transformer, that is across the RL. Okay, so we know that two familiar equations in transformers, that is V2 by V1 is equal to N2 by N1 and I2 by I1 is equal to N1 by N2. Okay, from these two equations we can simply modify, we can simply get the IPN value, that is the crime, that is the current across the load resistance, and VP by N value. At load, Vp by Ip is equal to Ip into N or L. So at load side, what have to do? Generally we know V by I is equal to uh, RL. Okay, V by I is equal to R. Okay, R is equal. So here V sense Vp by N. I sense Ip by N. So here Vp by N is equal to, then from that equation Vp by N Ip is equal to Ip into N or L. So Zin is equal to Vp by Ip. So Vp by Ip is equal to N square into RL. Okay. N is equal to Rs by Rl, square root of Rs by Rl. We assumed ideal transformer does not exist because due to the this ideal transformer does not applicable in practical conditions due to the losses which are going with due to the copper and core losses. We are going for another matching network. So due to the losses we are going for another matching networks. Okay, another matching networks. So here Only at these frequencies F1, F2, etc., the input impedance of uh, entire network is equal to RS. Entire network is equal to RS. The input impedance of entire network is equal to RS. At other frequencies, we don't know. Here, F1 and F2 are only discrete frequencies. Here, discrete frequencies. Here, another circuit is given, that is, here another network is given, that is or LC series network. Now we can transform parallel CL network to series CL network at chosen frequency. Okay, at resonance we have to, we know that already. At resonance, LP value, RP value, CP value simultaneously, the inverse of that parallel values or series values. Okay, or series values. So here at resonant, rs is equal to rs is equal to rp by 1 plus q square, and cs is equal to cp into 1 plus q square by q square. Rp is equal to rs into 1 plus q square. Cp is equal to cs into q square by 1 plus q square. Rp is equal to again rs into q1 plus q square. Okay, so lp is equal to ls of 1 plus q square by q square. So here series and parallel inductance, resistance and capacitance are all are inverse. So here also same, we are taking LR network and we are converting into parallel LR network, and we are converting into series network. And this series network, by simply substituting L value in series and RL value in series. Okay, so simply with this design, it works if RL is greater than RS. If RL is lesser than RS, it will not work. So we need to design another network. Okay, so now another circuit, matching circuit is there. We can design these matching networks at various shapes, that is L and C are connected in series or parallel with L section, T section and pi section. So these elements are connected in T shape, then it is known as T match. When these are connected in L shape, these are known as L match. And pi shape, pi match. Okay, so which shape we have to match that network, that match will be used. Okay, so that match will be perfectly suitable to that network. Okay, so here also this network works where if the condition is series resistance or source resistance is greater than RL. Okay, so remember this point here in this circuit. So we are taking the RL value in numerator and RS value RS L dash C is equal to 1 by omega naught square. Q is equal to square root of RS by RL minus 1. L is equal to Q into RL by omega naught. C is equal to Q square by omega naught square into 1 plus Q square into L. Based on the shapes, these networks will be based on different shapes. These networks are called L match if they are arranged in L shape, L match if they are arranged in T shape, T match if they are arranged in pi shape, and then it is known as pi match networks. So, what are passive components? Which does not need any power supply to operate, which can only receive energy, which it can either dissipate, absorb, or store it in an electric field or a magnetic field. Common examples of passive components include RLCM White's diodes. Okay, the structure or symbols for that one are given here. So what is active? So what is active? It needs power supply to operate. Common examples for active components include BJTs, different types of transistors, BJTs, MOSFETs, FETs and JFETs. So what are resistor, or you make a resistor on an integrated surface. So not all IC technology directly offer resistors, but RF process is do resistors. The modern resistors are made out of polysilicon, then the same material which is used for the set of MOS transistor. The top and side view of resistor is given in the track given in the track. So top view of the track is like this and the side view of the track is like this. It will be having the length, it will be having the width and height. The polysilicon material has resistivity rho. The cross sectional area A is equal to W into H. W is equal to width of material. H is equal to height of material. So here the polysilicon material having resistivity rho, the cross-sectional area A is given with the W into H. W is equal to width, H is equal to height. In this case, resistance is inversely proportional to the cross-sectional area of the material and it is directly proportional to the length and resistivity rho. That's why here given it as R is equal to rho L by A. Okay, rho L by A means A in A space we are writing H into width. Okay, here units of rho is ohm meter. Okay, with the track like this, we can make 100 ohm resistor. If we want 1 kilo ohm resistor, then we will usually make lot of tracks, put them in a snake-like fashion. Okay, with the track like this, we can make 100 ohm resistors. If we want 1 kilo ohm, then we usually make lot of tracks, put them in a snake-like fashion. Okay, the shape is given below. Here the L by W squares, length by W squares. So length is divided with width. Okay, length is divided with width. So in each track length and width, the number of squares in the track represents the resistance of the track. Okay, friends, thank you.